Alright, so this is our first video of chapter 12. Let's think about what we're going to do. So, to put it in context or in order, in the previous chapter what we were doing is we basically learned about the forces that things felt when they were in a magnetic field, specifically a charge or a current. And we learned about the right-hand rule too. In that chapter we did mention the fact that a current will create a magnetic field, but it was pretty general. We didn't really get into any specifics. Well, that's what we're doing in this chapter. We're going to think about and learn how we can calculate the magnetic field caused by different currents and shapes of current carriers. And what I want you to think about when you think about this chapter is, in the first half, we're going to learn how to find the magnetic field due to a current in the hard way. And then in the second part of the chapter, we're going to learn how to do it the easy way. So, in general, thinking about some of the specific things that we're going to look at, and I forgot to change this. This is chapter 12, sorry. We're going to look at how to calculate the magnetic field produced by a straight current carrying wire. We're also going to look for the magnetic field due to a current carrying wire that's in a circular shape. We're going to talk about how wires that carry current in the same direction attract each other, and that wires carrying current in the opposite direction repel. And then finally, we're going to learn about Ampere's law. And Ampere's law is going to give us the easier way to calculate the magnetic field due to a current distribution, but as we found with Gauss's law, there's some restrictions, and the current distribution has to be symmetric. Okay, so we're going to start off with this picture right here. And this is a picture from your book. It's a piece of wire, and we're going to try to think about the current caused by this little piece of current, the magnetic field caused by this little piece of current right here. And we're going to look at this location. Because we're just taking a small piece of the current wire, we're going to call that DI. And because we're looking at the magnetic field that little piece produces, it's called dB. So you could think of as delta I and delta B if it makes you more comfortable. But the other things to notice on this picture is we go from the piece of current and we draw a line from that location to where we want to find the magnetic field. The distance that between the two is r, and the unit vector, remember what a unit vector is, that has that funny hat on it. It has a magnitude of 1, and all that it's doing is showing the direction. Okay, so in order to figure out how we would use all this information to calculate the magnetic field caused by that piece of wire, we need to sort of make some observations, like how big is the magnetic field, what causes it to increase, what's the direction, etc. And so some of our observations about the magnetic field, I'm just going to put that to remind us. One of them is that the magnetic field is going to be proportional to the current. And what I mean by that is the larger the current, the larger the magnetic field that's going to be produced. This picture is a little bit difficult to pick. I don't know, I find the geometry of this picture a little hard to visualize, but if you remember from last chapter, we did talk about the fact that if you lay your thumb in the direction of the current, the way that your fingers wrap around your thumb is the way that the magnetic field wraps around the current carrying wire, because it makes circles around it. And so when we see the X over here for the magnetic field, that says that it's going into the page. And so when we put our thumb in the direction of the current, our fingers on that side of the wire would point into the page. And so what that means, if you think about it, then the little vector that represents the current, the DI, and the little unit vector R hat that points towards the location where we want to find the magnetic field, it turns out that the magnetic field at that location is perpendicular to both the DI and the unit vector. And then also, something that we might not know, but I'm going to tell you and you just believe me, is that the strength of the magnetic field is inversely related to the distance squared. So as the distance gets larger, the magnetic field is going to get weaker. So this expression, we might not have thought about it, but this expression really does sort of, it encompasses all those things that we mentioned. It's 1 over r squared, so that's there. It's proportional to the current, and then it's perpendicular to DL and r hat. And one of the things that we learned about with the cross product is if you take two vectors, they lie in a plane. DL and r hat are lying in the plane of the page, but the magnetic field is perpendicular to the page. And so it ends up making sense that we could express the direction of the magnetic field by crossing the line segment in that direction with the r hat. So that's where that comes from. And then the only other thing here is the mu naught over 4 pi. That's just a constant of proportionality. It literally, those are constants. The mu naught is called the permeability of free space, and it's equal to 4 pi times 10 to the minus 7. So it's a constant that you want to remember. So this is the vector expression for the magnetic field, and then this would talk about the magnitude, and that would be, the magnitude of dl cross r hat is just dl sine of theta, because the magnitude of r hat's just 1, so we don't bother writing it. And so this is how we see the magnitude. So this is called the law of Biot-Savart, and it describes how we can calculate the magnetic field due to current. Of course, what we would actually end up doing if we wanted to calculate the full magnetic field is we would integrate this expression to find, so that we would be using the entire piece of current. So here is a little example, and I just thought I would do it as an example in the video, where we're trying to find the magnetic field due to a short piece of wire, where the current is, I think the current's going up, yep, in the vertical direction. And so we're trying to find the magnetic field here at this point, right here. And what we're told is we're looking at a little piece of the wire, and that piece of the wire only has a length of 1 centimeter. The current is 2 amps, and then we're looking at 1 meter away from the wire. So we had this expression on the previous slide. I'm just going to rewrite it in case you forgot it. And we're just going to use that to find this piece of the magnetic field due to this little piece of wire. We're going to call it delta B, and then we'll call dl delta L. Now, so we can start putting in values, but first of all, I wanted to write expressions for the sine of theta and r squared as they would apply to this particular problem. This length of this hypotenuse is really our r value, and then the sine of theta would be the opposite over that hypotenuse, so that would be x over the square root of x squared plus L squared, where that little l is the 1 centimeter. So if we substitute that in to my delta B expression, mu naught over 4 pi, we get I delta L, and then the sine of theta is going to be x times x squared plus L squared raised to the 1/2, and then r squared is going to be the x squared plus L squared, and then just like that, because r is the square root of that sum, and so if we square it, we're squaring a square root. Hope that makes sense. So simplifying it, we can write this as x squared plus L squared to the 3/2. And then if I want to substitute values in, this is 4 pi times 10 to the minus 7. Current is 2. The distance, the delta L is 0.01. X is equal to 1. And then 4 pi on the bottom. And then this is 0.01 squared plus 1 squared raised to the 3/2. And this turns out to be 2 times 10 to the minus 9 Tesla. So it's just a little problem example that I wanted to give. Oops. Sorry. All right, so now we want to look at a longer piece of wire, and we want to think about how we would look at this if we were doing the integration. So in this expression, as I'm going along, right here, actually, if I'm using my right-hand rule to figure out the magnetic field due to this long piece of wire that's horizontally along the x-axis, and at point P, if I do the right-hand rule, that's going to be coming out at me, is where the direction of the magnetic field is. And I would use this expression, at least to start off with, mu naught I dl cross r hat over 4 pi r squared. And so we're taking little pieces of the wire as we go along the length of it. And so just taking some arbitrary location right here. This is our origin. This is our r hat. And then this is the distance r from where the current is to where point P is. And then overall, the distance P is said to be a distance large r away from the wire, because remember, if you measure the distance from a point to a line, you always have to draw a perpendicular from the point to the line, and then that defines the distance. So a couple things here, if we look at it. Well, I'm going to rewrite this to write it in scalar form, because we already determined the direction of the magnetic field. So our r is going to be given by the square root of x squared plus r squared. So that's my distance from the piece of wire to the point P. dl, I might as well just write it as dx because it's along the x-axis. And then the sine of theta, you can see how theta is defined as r over the square root of, x squared plus big R squared. So if I substitute that into my expression for dB, I got mu naught I dx times r over 4 pi, and then the r squared plus this from the sine of theta is going to give me x squared plus r squared raised to the 3/2. And so normally the way that we would find the total magnetic field would be to integrate this, and that would give me magnetic field. My variable of integration in this problem would be x, and so it would sort of be from, the lower value of x, or the x value over here, to the x value on the right. But we want to look at a long wire. So we want it actually to be infinitely long, so that we would do this integral, our limits would be from minus infinity to infinity, and then all this stuff. But we're going to do a little trick, because it's symmetric. What we can do is we can just integrate from 0 to infinity and multiply this all by 2. So basically we're doing half of it, but then we multiply by 2, because basically the right-hand side of the wire is going to just add as much as the left-hand side of the wire. And so then our integral will be mu naught I r dx over x squared plus r squared raised to the 3/2. And that's going to give us, sorry, I forgot the 4 pi, mu naught I over 2 pi times r dx, 0 to infinity, of x squared plus big R squared to the 3/2. And then if we integrate that, we're going to get mu naught I over 2 pi r x over x squared plus r squared raised to the 1/2, evaluated at 0 and infinity. I know, it's a lot, and I'm leaving out a lot of steps because I know you don't want to see it. And when we do that integral, or evaluate it, mu naught I over 2 pi r, and then x over x squared plus r squared raised to the 1/2, evaluated at 0 infinity, we actually get this expression. And this is the expression for the magnetic field due to a long wire. So I know we said that our wire was infinitely long, but just for argument's sake, what we're doing is we're going to allow for if the wire is really long, so just substantially longer than the distance away from the wire that we're looking at the magnetic field, it's fine to use this. So you don't have to see a problem where it says it's an infinitely long wire. If it just says it's long, we can use this expression to find the magnetic field due to the current carrying wire. And you can see here that it's proportional to the current, so the stronger the current, the bigger the magnetic field. And it falls off as 1 over r. So as we go away from the wire, the magnetic field's going to get weaker. This is an expression that you're going to use fairly often, and so you're probably going to want to try to commit that to memory. So now we kind of go back to this picture that we saw in the previous chapter, where we talked about how when you have a straight current-carrying wire, the magnetic field makes circles around the wire. We use the right-hand rule to figure out what direction the magnetic field would point on those circles. And now we also know that the strength of this is mu naught I over 2 pi r, where the r is how far away we are from the wire. So let's think about using this for this particular problem. And this is one of the problems where I'm going to start it, but then you're going to have to finish it when we meet for class. So I think what's helpful here is, so we have a square, and we have 3 wires, and all the x's mean that the current is going into the page. And what we want to think about is, in general, the magnetic field lines due to each one of these wires is making a circle. And the magnetic field is always going to be tangent to that circle. And we have to think about, well, where do I want to know that magnetic field? Well, for all 3 of these, I want to know what it is at point P. Let's just start, because I drew a circle around I3. Let's start with that one. Now, the first thing we have to know is the magnetic field makes a circle around that wire, and the direction of it is either going to be, it goes around the circle in a clockwise direction or a counterclockwise direction. I'm going to have to use the right-hand rule, where I stick my thumb in the direction of the current. So I'm sticking my thumb into the page, and then the way that my fingers curl around my thumb is the way the magnetic field curls around the current. And so we see that for this wire it's going clockwise. And if I think of this circle hitting down here, that means that at this location the magnetic field due to wire 3 is going to be to the left, because when it's tangent to the circle it's going to be sort of perpendicular to that line between the current wire and point P, and so that's going to put it right in the minus x direction. Now if I do this for current 2, again I'm going to do the right hand rule, sticking my thumb in the direction of the current. My fingers are going to wrap around, and now again I'm going to get clockwise. These are all going to be the same because the current's all the same. For here, when I do the perpendicular, when I find the tangent, this is going to be my B2. So it's going to be at an angle because it's going to be perpendicular to this line that joins the current and point P. And finally, if you do current 1, you're going to get B1. And now I see all my B's are so close together, it's hard to see which ones they represent. But it's B3, B2, and B1. So once you know that, you have to find how big B1, B2, and B3 are, and then you have to add them as vectors, which means you're going to have to find components, add like components, do the Pythagorean theorem, find the angle, all that. But that's what I'll leave you to do when we meet in class. So that's the first part of chapter 12.